Today we are going to take a closer look at yet another radionuclide, Technetium-99. This vial here has a very interesting history which I will get to shortly. But first let's see what we have here. This is an aqueous solution of ammonium pertechnetate. This solution contained approximately 2 grams of ammonium pertechnetate with an activity of 1 gigabecquerel when dissolved. Wearing gloves is an absolute must this time, as it's practically impossible to decontaminate the vessel, especially the plastic cap, which is highly contaminated. I wiped it once with a tissue to avoid getting too much activity on the gloves, and listen closely. Yes, this tissue had about 400 counts per second, even though the bottle was sealed. The pertechnetate ion, which resembles permanganate, is extremely mobile, meaning it disperses rapidly in the environment, including deep into plastics. So what makes this bottle so special? Take a closer look at the ordering date, March 2nd, 1965. And it comes from Oak Ridge. Not only is it very old, but it was ordered by the institute founder Wilfried Heer. He was a PhD student under Otto Hahn. Otto Hahn, together with Fritz Strassmann and Lise Meitner, he discovered nuclear fission. He is considered a pioneer of radiochemistry, and this bottle is connected to the beginnings of nuclear chemistry. I would love to make a separate video about the discovery and the use of this bottle, but this will have to wait a bit. Today our focus is primarily Technetium-99 itself. So let's start with the decay data so that the most important information is clear up front. Here's the decay scheme. Molybdenum-99 is radioactive and decays 82.4% into technetium-99m, an excited state of technetium. This state is relatively stable with a half-life of 6 hours, so we can call it a metastable state. This technetium-99 can decay into the ground state, emitting a 143 kiloelectron-volt gamma quantum. But it doesn't have to. It can also undergo a beta-minus decay directly into ruthenium. These 143 kiloelectron-volt quanta originate only from technetium-99m and are used in medicine. So when most people hear technetium, they mean the relatively short-lived technetium-99m, which is used in medical application. Our technetium is not this technetium-99m, but rather it's in the ground state, so it's technetium-99g. This technetium-99g has a half-life of 210,000 years, decaying into ruthenium-99 with a beta energy of 84.6 kiloelectron volts on average and 297 kiloelectron volt maximum. The specific activity is about 633 megabecquerels per gram. Now where does it come from? Oak Ridge, but more precisely, the technetium in our lab is purified fission material. When uranium-235 undergoes fission, the yield of the 99 isobar is about 6.1%, meaning a lot of technetium accumulates in such reactors. 2 grams per day per 100 megawatt hours, to throw in some numbers. Looking at the gamma spectrum, you can see that the two technetium-98 lines at 652 and 745 kiloelectron volts are present. Wait, we were talking about technetium-99. What's with the technetium-98? Well, it's fission material and it's long-lived enough to be present in the technetium sample. And while we're on the subject of fission products, the well-known cesium-137 is also present. It has a half-life of 30 years, which is about 1/10,000th of the technetium-99g's half-life. I should go further into detail when it comes to fission. So when you do nuclear fission, for example with uranium-235, uranium-235 is a very neutron-rich nucleus. And when this gets split, the fission products will also have a very high neutron access. And what a nucleus can do when it has a very high neutron access, it can either do neutron emission or it can do beta-minus decay. They will continue to do beta-minus decay along the isobar until they reach the value of beta stability. Fission products about the mass of 90 to 100 are quite common. Why that is, I would explain in a separate video. So, when you, for example, have a strontium-99 nucleus, it will continue to do beta-minus along the isobar until it reaches technetium-99. And all the other isotopes along the isobar will eventually end up into technetium-99. This, with a half-life of 210,000 years, is quite stable for human lifetimes. So every nucleus with the mass of 99 that is a fission product will eventually end up forming technetium-99. You can then describe how much technetium you will get out of your fission by a term called cumulative fission yield, because every 99 nucleus will end up into technetium, accumulating this technetium-99. This is not the case with technetium-98, because if one nucleus with the mass of 98 is formed, it will end up into molybdenum-98, which is stable and will not decay, forming technetium-98. So only if the fission will form technetium-98 as a direct fission product, only then will you have technetium-98, which was not the case for technetium-99. In order to describe how much technetium-98 you will get, the cumulative fission yield for the 98 isobar will be quite useless, as none of the 98 nuclides will end up forming technetium-98. So the 5.7% cumulative fission yield are quite useless when you want to describe how much technetium-98 you got. So you gotta use the direct fission yield, which is much lower. So in conclusion, technetium-98 can also be present in your technetium sample if it was made from reprocessing spent nuclear fuel, but so can also be the cesium-137, but this is not because of fission physics, but because of chemistry. So if the sample isn't at least 99.99% pure, the activity of the entire sample will still be dominated by the tiny cesium-137 contaminations, which could be present. How does technetium-99 get out of the reactor? After all, it's spent nuclear fuel. Ideally, it goes through the Purex process, plutonium recovery by extraction. TBP and kerosene are used for this, extracting plutonium, uranium and trace amounts of neptunium. I will make a separate video about this process. Ultimately, the remaining material is removed from the solution through a scavenger precipitation. This involves iron hydroxide precipitation with ammonia at pH of 2.5. After all these steps, you have a fairly pure ammonium pentactinate solution. Only if tiny amounts of cesium-137 sneak in, you will see them immediately in the gamma spectrum. And this is how we go from radioactive reactor waste to our technetium-99 stock at the university. This method is very effective if you want technetium-99G. Medically used technetium-99M is produced differently, but now you have a glimpse on the difference of technetium-99M and technetium-99G, where we got our technetium-99G, and many more technetium videos will follow. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Stubb and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, goodbye!